Hi, everyone. I'm Ben Walker, a technical lead at Intel and one of the core maintainers of SPDK. And I'm going to be presenting along with Thanos Makatos from Nutanix on virtualized NVMe devices with a new specification and protocol called VfioUser. So here's the agenda for the talk right now. We're going to start with a short bit of history that is mostly taken from my memory, and I don't promise that it is accurate. Then we'll talk a lot about standardization of the new VfioUser protocol, its adoption in QEMU, and the utility libraries produced by Nutanix for making it easier to use. And then we'll go into emulating NVMe devices and how we did that in SPDK. So this whole thing started, if my memory serves, years ago, sometime around 2016, possibly, with some discussions at the various storage conferences, the SPDK summit, the initial SPDK summits, SDC, FMS. People involved were Felipe Franciosi from Nutanix, myself, Jim Harris, there were others, where we were talking about some of the challenges, particularly with VirtIO block and VirtIO SCSI and the extra overhead and really the desire to get virtualization to the NVMe protocol so that we could run standard drivers. That was really the goal, is we wanted the guest OS to be able to run regular old NVMe drivers for these virtualized devices to help with enabling, and then we still wanted it to be very fast. So this went on for some time. We talk about it every time we saw each other. There were some initial attempts at solutions in this space. There was a brief attempt at VirtIO PCI, which was rejected. There was another attempt at VirtIO NVMe, which is NVMe commands inside of VirtIO descriptors, and that got enough traction that the SPDK team, Changquan Liu, implemented it, but it didn't really get enough traction to move forward. The most promising one was when Nutanix at, I believe it was KVM Forum, demonstrated a method to fully emulate any PCI device from an outside process into QEMU using Linux's existing MDEV mediated device framework. And it worked, but it was initially rejected for political reasons. The concern primarily from the QEMU community was that if you move the device emulation out of QEMU, the code running in those other processes could be licensed differently than GPL, like QEMU is. And so it loses some of the open source stickiness of QEMU. And they would prefer to keep the emulation inside of QEMU codebase itself. So anyway, we sort of stuck with it, to continue on, because we needed this, and we needed the performance this would provide and the flexibility this would provide. So at one point, I traveled to the Cambridge campus for where Felipe, Thanos, and others work. And over the course of 2 days, we hacked up a prototype to use their MDEV framework to emulate an NVMe device using the SPDK NVMe over Fabrics target. And we're going to talk about that in the second half, about exactly how we're doing this. So this seemed to work quite well, at least well enough to show that this was real. This sort of came together with some other community work from Oracle to build a multi-process QEMU, where they sort of had the same challenges, where they need to do parts of QEMU off in separate processes. And sort of the momentum came together all at the same time to push the initial political rejections out of the way and move forward on officially standardizing this approach. Now, sometime during that discussion and effort, the approach actually changed, and it shifted away from the mediated device framework that is in Linux today to a new VfioUser protocol, which is a protocol that is transported over a Unix domain socket, and that doesn't require any kernel changes or kernel support at all. And so Thanos will talk about the details there of why that is and how it works coming up. And so, at this point, Nutanix open source libVFioUser, which we're going to talk about, and SPDK later open source full emulation of NVMe devices that can be presented into QEMU. So this is sort of the timeline of what happened, and now we can go through the details of each step. So with that, I will hand it over to Thanos.
Thanks, Ben. Devices are typically emulated within the QEMU process, and this has many advantages. However, there are cases where it makes sense to move device emulation into a separate process. By doing so, we can emulate devices from a single process to multiple guests. And this enables polling, which is otherwise prohibitively expensive. By polling from a single process, we can greatly improve performance and CPU efficiency. Also, device emulation outside QEMU offers greater security and stability. For example, a device can be implemented in a safer programming language, such as Rust. Device emulation can be restarted after a crash, and device emulation can be seamlessly upgraded without having to upgrade the whole QEMU process. VfioUser protocol enables out-of-process emulation. It evolved out of the MUser framework, which was initially conceived for SPDK. The VfioUser protocol is based on Linux's Vfio Framework, which stands for Virtual Function I/O. VFIO is a mechanism for allowing a physical device to be passed through to a user space application, and that application can be a QEMU guest. The VfioUser protocol is based on VFIO mainly for two reasons. First, VFIO commands and structs do exactly what we need. And second, we can largely reuse the existing VFIO client implementation in QEMU. VfioUser is like vHostUser, which is a mechanism to allow out-of-process device emulation for virtio devices. However, VfioUser is not specific to virtio or particular kinds of devices or buses. The VfioUser protocol is independent of QEMU. However, QEMU is its primary use case. VfioUser is still in development. The current patch revision is version 9 and can be found at QEMU Develop. The protocol is a simple request-response protocol that defines a set of commands and their message format. In the protocol, we have the client, QEMU in our case, which initiates most of the commands, and the server, which is the process where the device emulation runs. In this table, we see the core commands of the VfioUser protocol. The version command is used during initialization to ensure that both QEMU and the device understand each other. QEMU uses the DMA map and DMA unmap commands to tell the device that it can DMA to a particular memory address in the guest. The device getinfo command is used to query general device information. For example, how many device regions the device has. Information specific to a device region is retrieved using the device get region info command. Device get IRQ info is used to query the device about the interrupts it supports. Region read and region write are used to read from or write to a device region that isn't memory mappable. For example, the PCI configuration space is never memory mappable. Similarly, the server uses the DMA read and DMA write commands to read from or write to guest memory when QEMU doesn't want its memory to be mapped into the device process. QEMU uses the device reset command to reset the device. And finally, the dirty pages command is used to retrieve from the device dirty guest pages, which typically occurs during live migration. Now let's take a look at the message format. Each VfioUser message is prefixed by a 16-byte header. The header carries the message ID, which is a value private to the sender and is echoed back in the response. Next, there is a command field, message size, including any payload, and then there's flags and the error field, which is set in the response in case of error. Most requests have a payload. For example, here's the payload of a VfioUser DMA map request. Args is a field inherited by VFIO and has special meaning. Usually, it's the size of the payload of the maximum size of, or the maximum size of the response. The flags fields, which indicates whether the region is readable and writable. The offset field, which is the absolute file offset if there's a file to be memory mapped. And the address and size fields, which is the guest physical address being mapped and its length. Now let's look at libVFioUser. The difference between VfioUser and libVFioUser is that VfioUser is a protocol, while libVFioUser is a user space library that does two things. First, it implements the server side of a VfioUser server, and second, it provides a framework for emulating devices. When we use libVfioUser to emulate a device, the VfioUser protocol and client details are completely hidden from the user of the library. libVfioUser is maintained by Nutanix. It's a relatively small library written in C, and it's BSD licensed so that it can be used by SPDK. Here's how libVfioUser and QEMU work in practice. To the left, we see a QEMU guest, and to the right, we see an emulated device based on libVfioUser. The low-level components of QEMU and the device communicate over a Unix domain socket. Through this socket, they exchange VfioUser messages, which allows setting up event FDs for triggering interrupts, making device regions memory mappable into the guest. For instance, the guest can memory map bar0 for doing MMIO, and finally, making guest RAM available for memory mapping into the device's address space for doing DMA. For instance, checking an NVMe submission queue. Emulating a device with libVfioUser is relatively straightforward. First, the user of the library describes the device regions. For instance, their size, whether they're readable, writable, or memory mappable. And if a region is memory mappable, the user indicates whether it can be memory mapped entirely or in parts. Next, the user defines device behavior by providing various callbacks. These callbacks are executed when a device region is read from or written to by the guest, when the device is migrated, and when guest RAM is added or removed, which we explain why it's needed in the next slides. Finally, the user describes what kinds of interrupts the device uses, for instance, how many MSIX interrupt vectors it supports. libVfioUser simplifies emulating a device in the following ways. It handles the entire PCI configuration space and PCI capabilities. It simplifies DMA by automatically making guest memory available in the device process and by providing an API for translating guest physical addresses to local virtual addresses. It makes it trivial for the device to trigger an interrupt, as the user only needs to specify the subindex to trigger the interrupt on. And finally, migration is made easier by handling most of the complexities and by executing user-provided callbacks that manage device state and handle migration data. Using libVfioUser, we can write an emulated GPIO device, which is a simple device with an external pin that is either 0 or 1 in less than a few dozen lines of code. Here's a slightly simplified example of how libVfioUser is used in practice. First, we create a libVfioUser context, which is an opaque structure and is passed to most libVfioUser functions. Next, we configure the device to be a conventional PCI device, set the PCI device and vendor IDs, and add the power management capability. We then configure bar0 to be 16 kilobytes in size and set up a function to be called whenever the client accesses bar0. We then configure the device to use intex and then provide callbacks to be executed when guest RAM is available for DMA. Next, we finalize device creation and run device emulation. From this point, the device is usable by the guest. We'll now explain why the device emulation needs to be told when guest RAM is available for DMA. When QEMU tells a device that some of the guest memory can be accessed by DMA, it sends a file descriptor so that the device can memory map it. This memory mapping is done internally by libVfioUser. However, mapping the guest memory is not enough for doing DMA because the memory layout is different between the guest and the device. libVfioUser contains a software memory controller that provides an API for translating guest physical addresses into local virtual addresses. In this example, the device passes a guest physical address to function VFU address to segment, which fills in a DMA struct. Note that the device indicates whether it needs to write to that address. This is important because this is how libVfioUser tracks 30 pages for live migration. The device then calls function VFU map segment to get a pointer in its own address space, goes about its business, and then finally unmaps that address. We're planning to spin off the DMA controller as a separate project. Support for live migration is a recently added feature in libVFioUser. In VFIO, live migration uses a special device region, the migration region, which must contain at the beginning some specific registers. libVFioUser uses this mechanism and provides an optional API for simplifying live migration for the device. To enable live migration, the user must set up the migration region and provide certain callbacks that are executed by the library when the device is live migrated. These callbacks are the device state transition callback, which is executed when the guest changes the device's migration state. These main states are the running state, which is the default state. At the source, we have the pre-copy state, where the device is still used by the guest, but QEMU copies migration data in the background, and the stop and copy state, where the device is not used by the guest, and QEMU copies the remaining migration data. In the meantime, at the destination, we have the resuming state, where QEMU receives migration data from the source QEMU and writes it to the device. When it's done, it switches to the running state. The next callback is the get PendingBytes callback. During the pre-copy and stop and copy states, QEMU executes the get PendingBytes callback, where the device gets to tell QEMU how much migration data is left to be copied. QEMU then proceeds with reading this data, either directly from memory if the device chooses to make the migration region memory mappable, or by executing the read data callback, where the device returns a buffer with the data. QEMU keeps doing this until the device returns 0 from this callback to indicate that there's no more data to migrate. In the meantime, at the destination, QEMU calls the prepare data callback, where the destination device tells it where to write the migration data. Then QEMU proceeds with either writing the migration data directly to the migration region, if it's memory mappable, or by calling the write data and data written callbacks to explicitly provide the migration data to the device. It repeats these steps until all migration data have been written. We're still at the beginning of making device emulation easier with libVFioUser. First, we want to make the library more stable and add more automated testing. Also, we need to make use of the ongoing work on I/O region of D in KVM that allows for faster MMIO when a device region isn't memory mappable. Another area to improve on is the client using a virtual IOMMU. Although this is a VfioUser client matter, we can certainly do more in libVFioUser to make the IOMMU more performant. Better PCI support would be nice to have, for instance, handling more PCI capabilities or supporting PCI bridges. Multi-threading is also on our list, since some of libVFioUser functions are not thread safe. Finally, making device emulation restartable would be great, since that would give us better resilience and would make upgrades more lightweight. Finally, I'll provide a brief overview of the corresponding changes in QEMU that enable VfioUser. This work is led by the multi-process QEMU team from Oracle. It's a relatively small adaptation of the existing VFio client in QEMU. These changes are not merged upstream yet. Multi-process QEMU uses the libVFioUser protocol, where the libVFioUser server is again a QEMU process. The multi-process QEMU team have ported the LSI SCSI controller from QEMU to libVFioUser and are now working on enabling live migration. Using VfioUser in QEMU is simple. First, we start the device emulation process indicating the socket to create, and then we start QEMU passing the device VfioUser PCI option, telling it where to find the socket. That's all for VfioUser and libVFioUser. Back to Ben now.
Thanks, Thanos. That was great. Awesome detail there. Let's talk a little bit about how SPDK now uses all of that great infrastructure to emulate an NVMe device. So as we were thinking through how to emulate storage devices using a mechanism like this, we realized very quickly we were going to have to write code, or thought we would have to write code to emulate a physical PCI NVMe device. And there were a lot of different thoughts about how we do that, which parts of various libraries that were around that we could possibly reuse. But it became fairly obvious, I think, early on in the discussion that the best target was the SPDK NVMe over Fabrics target. So for NVMe over Fabrics, to implement that protocol, even though it's a network protocol, it requires the server side to mostly emulate an NVMe device. It's not exactly the same, and we'll cover some of the differences in the rest of this section. But it is very close. So most of the work was already done in the NVMe over Fabrics target in SPDK to emulate an NVMe device. What we had to do was swap out the existing transports for a new one. And so this is the general approach. NVMe over Fabrics defines pluggable transport layers. They already define TCP, RDMA, fiber channel. The new version of NVMe 2.0 even counts PCIe as a transport, defined just like the others. So what SPDK is elected to do here is add another one. And this is a non-standard transport, but it fits in just like the others in the code. And it's the VfioUser transport. And it's a shared memory transport. So it is a shared memory or a virtualization transport that plugs into the transport plugin API of the SPDK NVMe over Fabrics target. The current NVMe 2.0 spec defines two types of transports that you can create or define. One is a Fabrics transport, which is historically what there's always been, networked based. And the other is a memory transport, which is only PCIe in the spec. This transport happens to be much more like PCIe. It is mostly a shared memory transport. Fabrics and memory transports do behave differently, even in the spec, and that's called out. There's an order of operations issue, and so our existing transport plugin API in the NVMe over Fabrics target did have to adapt a bit to handle memory-based transports. But it worked out great. You know, by the time I think we got through all of the patches, the final patch to just add VfioUser as a feature to SPDK only added a new transport. It didn't touch any of the rest of SPDK at all. So the new NVMe 2.0 specification, I just want to pause and talk a little bit about the reorganization that's happened and is now live in the NVMe spec. It's excellent. They've sort of retroactively fit a lot of the concepts that have emerged out of NVMe back into the organization of the specification now. So if you go onto nvmexpress.org and you look at the specification documents, you'll see that now there's a base specification which talks about general purpose NVMe things, and then there's individual documents talking about each of the transports, which includes PCIe now as one of the transports. And so the spec now mirrors really what the structure of SPDK and the implementations in the Linux kernel actually look like in practice. And I think it's really fantastic. And so they've called out that there are different categories of transports, like I just described, as a memory and a Fabrics. And this is a new one, the second one that I've seen, second to PCIe, of a memory transport type. So as we were doing this, making these adjustments to support memory transport types in SPDK, we definitely ran into a couple of issues that we had to deal with. One of them is that the listener concept that we have in a fabric-based transport is different for VfioUser. It would be different for PCIe as well. There isn't like a network endpoint where a server is listening and somebody else connects. There is a Unix domain socket here that we connect to and can listen on, but there's only ever a single host that's connected on the other end. This isn't like a listener that's getting reused and discovering new connections, right? It's point to point. So we had to make some adjustments to that code to handle this case. You know, when you can add a listener to a subsystem in VfioUser using the same JSON RPCs that you would use for other transports in SPDK, but that listener can only have one thing connected to it at a time. So also interesting is we don't have to be polling now to accept new connections. We just sort of assume the other side is there. So it sort of skips some of the steps. Also, the name listener becomes confusing when it's not network based. So I think we probably need to change the name to endpoint to generalize that name, but at least the functionality is generalized. All right, and then another major area that fabrics differ from memory is in how the register accesses are performed. So in fabrics, registers are accessed using commands that are sent on the admin queue, fabrics get and set property commands. But for a memory transport, they're done with typically MMIO. You know, you have a bar and the client is reading or writing to the bar, and that generates, you know, traps or requests back to the server or to the device in the case of PCIe. So libVFioUser has excellent support for this. You know, we can have a thread that is blocked on a file descriptor that gets woken up every time there's MMIO. So essentially we get an interrupt on the server side. But the NVMe over Fabrics target doesn't know how to do MMIO. It knows how to do Fabrics get and set property commands. So what we do is when we detect the interrupt for a MMIO operation, we, in the libVFioUser transport in SPDK, we generate a fake Fabrics property get or set command as required. If it is a MMIO read operation, then we will block in the thread that was handling MMIO for that request to get processed and only return back when we have the read response. So you actually have the 4 bytes or 8 byte MMIO data that you tried to read when it returns. For a write, these are posted just like a real MMIO write would be. So they send the command to write it and then they return immediately. So it behaves just like a real device in that sense. Then we also immediately ran into the issue that it's not just the mechanism of the register reads and writes that's different between the two. It's actually the set of, you know, the ranges in the bar that are accessible or readable or writable is different between a memory transport and a Fabrics transport. There's just different registers that you are allowed to set or get. So we had to expand support for a wider range. That was relatively easy. And then another major challenge is the order of creation of the admin queue is reversed in a memory-based device versus a Fabrics-based device. So in a Fabrics-based device, first the client connects to the server. They establish an admin queue, which is the first connection. And then it sends register reads and writes on the admin queue as Fabrics get or set property commands. But in memory controllers, first it does MMIO to set the controller up, including set up the admin queue, and then it turns the device on, which creates the admin queue, and it can send commands on the admin queue. So the question becomes, for the MMIO occurs before the device has been enabled, how do we generate a fake Fabrics get or set property command on the target side if there is no admin queue yet, right? These have been done in reverse order. So the solution right now is that the transport, whenever a listener is created, hopefully soon renamed an endpoint, just automatically creates an admin queue. We know there's only going to be one client effectively on the other side, unlike a real Fabric. It's sort of single tenant, like a real single port NVMe PCIe device. So we create the controller right away. We create an admin queue right away, and they're just internal to the SPDK transport at first. And then we start getting MMIO and we send them on this admin queue. And then eventually the user will tell us where in guest memory where they wanted the admin queue, you know, submission queue entries and completion queue entries to live. And when we see the MMIO write for controller enable, we'll go look at the registers they had written for the admin queue, locations in their memory and will memory map those into the device space and update our structure internally from, pointing at a dummy region of submission queue entries to the real ones. And so that's how we sort of work around the ordering issues. And it works out quite well. So once we got through those major issues, it worked, right? Like an NVMe device appears, you boot up QEMU, and you point it at this this Unix domain socket, and once QEMU boots, you see the NVMe device, and you can run the NVMe CLI tool, and it thinks it's a real NVMe device. All software that works on NVMe devices works. And so we were able to push some of the general infrastructure changes to SPDK ahead of time and get those merged early. And so that the final patch that contained the VfioUser transport only contained the VfioUser transport. It didn't have to change anything else in SPDK. It was just a clean addition. So I think this was a great success for the code base, for the collaboration, for work with QEMU. I think it's fantastic. You can now run QEMU with a virtualized device, but the guest OS can just use its standard NVMe drivers. So this includes things like Windows booting with no extra drivers installed. So I also think this generalization is useful as a baseline for future additional transports that we expect to see over time for NVMe. Certainly, we expect to see the NVMe over Fabrics target from SPDK running as firmware on offload devices of various types, probably things like NICs, where it is pretending to be an NVMe device, and it is exposing, there's already products in the market for this, it's exposing NVMe devices to the host system, but those NVMe devices are logical devices. And we expect one good way to write that would be to just write a new transport for the existing SPDK NVMe over Fabrics target that interfaces with whatever mechanism or hardware is able to present the NVMe devices to the host. We expect other transports, maybe quick someday, if that ends up making sense. So we're very happy to have generalized this interface and to turn SPDK into what we think is a great NVMe emulator. And it opens up lots of opportunities to leverage SPDK to implement or prototype NVMe features, expose what looks like a real physical NVMe device to QEMU in a way that you can iterate and test, and if it crashes, everything's fine. It's a user space process. So with that, I want to say thank you, and we'll open it up to questions.